Section 26.2, Snell's law and the refraction of light. Snell's law is one of the big equations of this chapter. It says that when light travels from a material with one index of refraction to a material with a different index of refraction, the angle of incidence is related to the angle of refraction by n1 times sine of theta 1 is equal to n2 sine of theta 2. Now, what does this mean? Well, we could imagine we have a light source like this flashlight or laser that's being shown through the air, right? And we know from last chapter that when it hits the surface of the water, some of that light will reflect off the water, and it will reflect at exactly the same angle of incidence. So that's theta 1 there, which we note is the same on both sides. Theta 1 is equal to theta 1. But some of the light, because water is transparent, will also pass into the water. But as it passes into the water, the angle that it comes into the water at, or out through the water at, is different than the incident angle. So this is, theta 2 is known as the refracted angle, and it will depend on the relative indices of refraction here, n1 versus n2, where 1 is always the incident side and 2 is the refracted side. So let's take a look at an example of this. So example 1, determining the angle of refraction. A light ray strikes an air-water surface at an angle of 46 degrees with respect to the normal. Find the angle of refraction when the direction of the ray is from air to water, part B, from water to air. So we note here, and let me work on making this bigger. There we go. That the first key is drawing our picture. And for part A, it talks about the light ray is going from air to water. So it starts in the air and it hits at some angle, which we are assuming is not straight on at 90 degrees. Because once you get it at some off angle, that's where things become more interesting. So it hits the water, some incident angle, and note this angle is once again relative to that normal. It's relative to the perpendicular. I can also draw the reflected ray. So if you were asked about the angle of the reflected ray, you would know it has to be exactly the same as the incident angle, but then some of the light will also be refracted. There we go. So the refracted light is at another angle, which we call theta 2. And the reason we call this 1 and 2 is that's the 1 side versus the 2 side, where we note that we started in air and moved into the water. That's a key detail, and drawing this out makes it a lot easier on yourself, because the hardest part about Snell's law is figuring out what all the variables are and what they correspond to. So this is an example involving Snell's law. N1 sine of theta 1 is equal to N2 sine theta 2. So we already have our theta 1 and theta 2 labeled. We now need to figure out our N1 and N2. So for air, that's going to be our N1. It's on the same side as the incident light. And that's something we could look up in that table, which to 2 sig figs, or even 3 sig figs, would be 1.00. Similarly, for water, we could look it up in that table, and we'd find that it is 1.33 for 3 sig fig values. And then they even tell us, so once you know the materials, you know the refractive indices, but they also tell us the incident angle is, that the water striking the surface at this angle of 46 degrees. So we're now just solving for the angle of refraction, which our angle of refraction is always going to be theta 2. So we've identified all the variables. Now it's just manipulating the equation to solve for theta 2. So I'm going to divide N2 to the other side. So I have N1 divided by n2. Sine of theta 1 is equal to sine of theta 2. And we're just about there. If I take the inverse sine of both sides, then we'll be home free. So do that to both sides, then I'll have an equation for theta 2, that theta 2 is equal to inverse sine of n1 over n2 times sine of theta 1, which we can plug in. Inverse sine of n1 we said is 1.00. I'm glad I wrote it down so I don't get confused. n2 is 1.33. And sine of that incident angle, 46 degrees. Okay, and plugging that into your calculator, you should get 33 degrees, assuming your calculator is in degrees mode. Now, what changes for part B? Because this is just part A. Well, for part B, it says that instead of going from air to water, we're going from water to air. So we could sketch that out too, because drawing just makes it a lot more apparent, more visible what's going on. So I'll send the light ray in here. And we know some of it will still reflect at that same angle. But now the reflected ray is in the water because that's what we're starting out at. And this is our theta 1 on both of these. And then the light ray is also going to refract as it passes into the other medium. And a cool trick here on drawing these is that we notice, we'll look up here at this example because it's filled in, when we're passing from a lower index of refraction to a larger n value, our angle gets smaller. So smaller n, larger angle, larger n, smaller angle. So here we're passing into a smaller n, so I expect a larger angle. And once again, we want to label that that angle is relative to the normal, because that's easy to miss and get confused on. Okay, once we've done that, now we can say, hey, look, theta 1 is on the side of the water, so now n1 is equal to my 1.33. Theta 2, or n2, is just going to be that of air, 1.00. So for part B, I can use my same equation, but I'm just going to flip my 1 and my 1.33. My incident angle is still 46 degrees. And so when you plug it in with the 46 degrees, you should find that it comes out to not 33 degrees this time, but 74 degrees. So that's a pretty notable change, especially considering that we only flipped it around the direction, right? We didn't see, we didn't change anything else except for what order we were sending it in. So let's reshare that window. Go. So there you can see the same result as well. Okay, and a cool application of this is rear view mirrors. I didn't actually know about this until I read about it in this book. That, you know, sometimes when you're driving, especially if you have a small car like I do, and someone comes up behind you with their big pickup truck that's lifted and has crazy big suspension, and they have headlights that are right in your eyes. They're reflecting off the mirror right into your eyes, similar to this image. Well, nowadays, new cars have a fancy thing that will auto adjust. But what'd you do if you are driving a car older than the past 10 years? Well, you reach up there and you flick it, right? And the whole mirror, boom, kind of pivots outward. And all of a sudden, they become way less blindingly bright. What's going on? Well, it's physics, like everything. So what happens is in the day setting, which is the default one, light from behind you in general, like from the car's headlights, comes in and there's a little transparent glass wedge. And so it refracts off the glass wedge, and then there's a mirror on the back, and that will reflect most of the light to get back to your eye. Some of the light will still reflect off the glass wedge and reflect at this interface between the glass wedge and the air. But most of it is just passing through to the mirror and back to your eye. Well, when you rotate it to a slightly different position, depending on the exact geometry of your setup, then it's able to rotate so that most of the light that gets transmitted to the mirror then reflects upward, not into your eyes. And all that makes it into your eyes is actually the small amount that reflects off of that glass surface, not the primary mirror itself. And so you are no longer blinded. It's a little less bright, you aren't able to see as much, but you're not blinded, which is a definite perk. Okay, another cool application here is the idea of apparent depth. So here's an example that highlights it pretty well, and that's finding a sunken chest. So it says the searchlight on a yacht is being used to illuminate a sunken chest. At what angle of incidence should the light be aimed? So I started drawing the setup of this. We have it. And they give us a good amount of information actually in the picture here. So they specify, they have our boat, we have air and water, and they even tell us those indices of refraction, that the index of refraction of air is 1.00 and of water is 1.33. And they show how the yacht, see this happy person on the yacht, people on yachts aren't necessarily happy. Having money doesn't make you happier. But that's another time, another story for another time. So the light shines in when it reaches the water, because water has the larger refractive index, it's going to go to a smaller angle. And so the light ray can illuminate this chest on the bottom. And they give us some quantities of distances. Yeah, they say the chest from the vertical there is 2.0 meters and at a depth of 3.3 meters. All right, so based on this information, we want to know the exact angle to aim our searchlight to spotlight this treasure chest, right? So you can be like, oh, look, there it is. There's the treasure. Now we can go dive for it. Well, so we're ultimately solving for the angle of incidence, theta I. So we'll note that on there because that's useful to be aware of. We know we have Snell's law as a tool. So that's another good thing to jot down, that, hey, we have this n1 sine of theta 1 is equal to n2 sine theta 2. We know our n values already. We have to figure out which one's 1 or 2. But we just need another angle. We can notice first that, okay, the light's coming from the ray, so that's gonna be our incident side, so I'll call air n1, water n2. For my theta 2, I can draw that in here as well into my picture. And I don't know it, but I do know some other dimensions, and I notice that they've given me a triangle here, right? Right, yes, it's a right triangle. And that's the key, because with a right triangle, we can relate two of the side lengths to that angle. Look, we have this angle, and then we have the side opposite it and the side adjacent to it. We do not know the hypotenuse here. So which one gives us, which trig function gives us opposite and adjacent? It is tangent. So tangent of theta 2 is equal to 2.0 meters divided by 3.3 meters. So theta 2 is equal to inverse tangent of 2 divided by 3.3, where the meters are just going to cancel out. And I realized this is not as big as it could be. There we go. That should make it a little bit easier to see. Sorry, the light's kind of right on, glaring on it, but there we have that. And so by solving this equation, you get an angle of 31 degrees. But wait, we aren't done yet. It'd be easy to stop there, but we remember this is just the resultant angle. We still need to find the incident angle, so we need to go back to Snell's law. And so that's where we can plug in. And there are a couple ways to it. One, you can solve for sine of theta and then solve for theta 1. But if you're comfortable with your calculator, I find it just as easy to do it all in one step. And it's the reverse of the equation that we had before. So it's theta 1 is equal to inverse sine of n2 divided by n1 times sine of theta 2. And so yeah, we can plug and chug there, which is shown in the slides. So I'll pop back to that. And there we have it, that when you plug and chug and solve away, you get that the incident angle is 44 degrees, which is not the same as the angle of refraction. So this leads to an interesting observation that the treasure chest, if you look at it, appears to be higher than it actually is. It seems like the treasure chest is somewhere actually above it at a smaller apparent depth. Why is that? Well, when we look at light rays, our eyes can't do physics. Our eyes just assume those light rays are coming in a straight line from wherever. So we imagine that the treasure chest must be higher for the light to come straight to our eyes. This is not obviously where the treasure chest is. So if you have an observer directly above the treasure chest, you can note that not only will the angle of incidence and refraction change, but the apparent depth will be different. And you can get the apparent depth, d prime, relative to the actual depth with just the ratio of n2 over n1. So n1 is the incident ray, where the object is the key detail. So that's where the actual light rays start, and then the light rays pass through to the observer. That's the side that n2 is on. And so from this, you can get some different conclusions. One is that treasure chests appear to be closer than they actually are. But we could look at another example, and that's on the inside looking out. So if you're a swimmer underwater looking up at the surface, someone holds a coin in the air directly above the swimmer's eyes. To the swimmer, the coin appears to be at a certain height above the water. Is the apparent height of the coin greater than, less than, or the same as its actual height? I want you to think about this for a moment, so go ahead and hit pause so you can reflect. Did you do that? Okay, let's check. So the apparent height is higher than the actual height. And why is that? Well, the apparent height is our d prime relative to the original height d, and the actual object is now in the air. So air is our n1, water is our n2. Water has a greater index of refraction than air, so it becomes larger. The apparent height becomes larger. So the coin appears further away than it is. If you go to grab it, you'll probably knock it down. He'll be trying to reach too high into the air. And this produces a side effect, right? That a slab of material can actually displace the light. It can offset it slightly. If you have a light ray passing through air and then it encounters a glass slab, the glass will refract it, and then it will come out, and incidentally, it'll emerge at theta 3 that's exactly the same as theta 1. As long as it's air on both sides, then it'll be the same angle as it was before. The only change is that it will now be displaced slightly. It'll be higher up from where it was before. So that's an interesting aside. And that has to do, that'll depend on how thick the glass is. Now you could derive Snell's law with some geometry here. I'm not going to get into this too much, but it has to do with the wavefronts, and when they encounter a medium like water, it slows them down. And so as they slow down, the light itself has to bend. That's sufficient knowledge to me. Okay, so let's do a check your understanding to wrap us up here. Fishing. So a man is fishing from a dock using a bow and an arrow. To strike a fish he sees beneath the water, where should he aim? Another man is fishing from the dock. He is using a laser gun that emits an intense beam of light. To strike a fish he sees beneath the water, where should he aim? So I want you to think about each of these, where the fisherman should aim. So go ahead and pause now. Did you do that? Okay. Trusting you. So for the bow and arrow, he should aim slightly below. The laser gun, he should aim straight at the fish. Why is that? Well, with the bow and arrow, the apparent depth is higher than the actual depth, so he needs to aim down to actually see it. But for the laser gun, the laser is going to bend with the water. So even though the light that he sees is bending, the laser light will bend too. And a place you've already seen this before illustrated is if you've ever had to stick a pencil in water. It's a little hard to see there. But it seems like the pencil is broken, right? It looks like there's this weird knock right on the line there, but I guarantee it's just a normal pencil. And it's this interesting effect that occurs because of the refraction of light. For me, with this fishing example, I always think of Gary Paulson's Hatchet. It's a book for kids. Nice read if you ever want to read it. But it's a kid who gets stranded in the Canadian wilderness with only a hatchet to survive. And he takes up trying to fish with a spear. And he starts going for it. And he keeps missing all the fish. Why? And it's not until he sticks his spear in the water that he realizes that his spear suddenly looks broken because of the refractive nature of light and water. And so he has to start aiming below the fish slightly, and then he has much tastier dinners. So that's what you can remember. Very practical lesson in physics today for whenever you next go spearfishing. Okay, we will wrap up there. Take care.